I'm in the middle of migrating the breadboards of my homebrew 8-bit CPU over to dedicated printed circuit boards. We created a program memory board in the last episode, so almost everything is on a dedicated PCB by now. Today I want to tackle the big missing piece, which is the ALU. It currently sits on the left side of the build on 6 breadboards, and it has a ton of chips and wires going all over the place. We're going to move all of this onto a dedicated PCB. And this PCB will sit on the second backplane that we're building up at the moment. Let's go draw a schematic. First, we need some headers to bring in the left and right hand side inputs. The first 2 chips at the bottom are 2 programmable logic chips. These are ATF16V8 chips that implement the logic operations. These chips take the left and right hand side inputs, plus the logic operation to be performed, and then produce a result. And they also produce a flag swap helper signal. One annoying thing about these ATF16V8 chips is that they have pull-up resistors at their inputs. So when nothing in the CPU drives the left and right hand side input signals, these chips will pull those lines high. However, on the register file backplane, we have pull down resistors for all the read data ports. So in order to not have the internal pull-ups here and the pull downs on the backplane fight each other and becoming a voltage divider, let me add 2 buffer chips at the input. We'll also want to display the logic operation on a bunch of green LEDs. One thing I would like to experiment with is to make all the LEDs on this PCB dark if the ALU isn't doing any meaningful operation. And I think the easiest way to do this is, instead of connecting the LEDs to ground directly on one side, is to connect them to ground through a transistor, through a MOSFET. And this MOSFET will then provide a ground for all the LEDs, and by turning that MOSFET on or off, we can control whether the LEDs light up or not. And by using an N-channel MOSFET towards ground, we get an LED enable signal that is active high. I think I want an active low input though, because most of the output enables we have in the system are active low. An inverter chip will nicely sort that out. By default, we'll pull that input low such that it is active and all the LEDs light up. Let me also give these chips some meaningful names such that you can easily tell what their function is. So that's a 1 input inverter and an 8 input buffer. On the next breadboard, we have the shift operation. This is implemented by a bunch of 74HC153 chips. And we'll also want some LEDs to observe the shift operation. Just above the shifting multiplexers on the breadboards, there's the carry operation multiplexer. This is yet another 4-input multiplexer chip that, depending on the carry operation, picks the carry input that the rest of the ALU will use. Let me also add a flags input header, such that the ALU can read the current flags from the CPU. And again, we'll want to display the carry operation on a bunch of LEDs. Then right next to the carry operation multiplexer, we have the 2 adder chips that perform the actual addition. Next up, on the breadboard just above, we're computing the flags given the current output of the adder. And I'm using a bunch of 2-gate versions of the logic chips because we weren't using all of the gates on the breadboard. And I'm pretty sure we're also going to want to look at the computed flags on a bunch of LEDs. And then, still on the same breadboard, we have the ALU operation decoder. I'm also adding a 6th operation bit here as a kind of spare, in case in the future we decide we want to have more ALU operations available. And it doesn't cost anything on the PCB. And we'll need a header for the operation input. And then on the breadboard just above all of this, we have the flag swapping multiplexers, which also double as an output enable. And I think we want to be able to observe if flag swapping is enabled, and whether the resultant flag's output enable is active. We'll be using some more green LEDs for that. We'll want to bring the result and the flag's output onto headers, such that the rest of the CPU can use the result. And then the final missing piece, on the topmost breadboard, is the condition matching circuitry that looks at the flags and checks whether certain conditions hold. And we'll also want to display the condition match signal on an LED. And I think that's all the chips and the LEDs we need. As a final step, let me add a header for the control signals and power. And then let me add the usual 10 microfarad capacitor and 100 nanofarad capacitors, roughly one per chip we have. And then as a final touch, let me add the usual logos. And I think that's the entire schematic for the ALU of my 8-bit homebrew CPU. I'm gonna give this a quick check and clean up off camera, and then let's move over to the layout editor. We have quite a few components to place. Let me roughly arrange them into groups that would make sense to keep together on the PCB. The left and right hand side inputs probably want to be close to the buffer chips that decouple them. The PLDs that implement the logic operation on the right hand side probably want to stay together. And the multiplexers implementing the shift on the left-hand side probably should also stay together. Then we also have the adder chips. Then we have 3 chips that compute the flags. And 3 chips that check whether a condition matches. And finally we have 3 multiplexers that produce the result and flags output. To enable or disable the LEDs, we also have a MOSFET and an inverter. And then finally we have a whole bunch of LEDs that indicate various status signals. And now let me roughly try to arrange these groups in a way that will make sense. For example, I think we can have the left and right hand side inputs at the bottom left of the PCB, just to get started. It looks like the logic operation PLDs could sit right next to these inputs. And then the chips that perform shifting of the left-hand side input should probably be close to the left-hand side input. And both the logic operation chips and the shifter chips feed into the adder. And then the chips that compute the flags only depend on the adder outputs. So these can be pretty close to the adder. I think it would make sense for the result and the flags output to be at the top of this PCB. Then maybe the operation input and the operation decoder can also be at the top. And then the condition matching basically depends on the flags input and also parts of the opcode, and it produces a condition match signal that the decoder wants to consume. So maybe that should sit in between the decoder and the result. Then let me try to move the chips a bit closer together. This looks like it might just work. This would be a pretty cool layout for the ALU, I think. Alright, now to the fun part. Let me actually route the signals. First of all, I'll try to figure out how the left and right hand side inputs can both go into the logic operation PLDs. Then let me figure out how the output of these logic PLDs can be routed up to the adder. let's see how the shift multiplexers could be wired up. Alright, that doesn't look half bad. Let me see if I can route some of the signals around the adder chips. And then let's see how the flags computation can be wired up. And let me bring the flags over to the flags output header. Let me bring the control signals over to the decoder. Then let me try to route the signals around the result headers. Then let me wire up the condition matching circuitry. Then let me wire up the control header. And then let me go clean up the silk screen a bit. That looks like a very nice PCB. We were able to squeeze the chips into a pretty small area, which is really nice. Let me order this up, and when I get it back from the manufacturer in just a few seconds, let's go assemble it. I've just received the stencil and the PCBs in the mail. Let me go and add solder paste to one of the PCBs. And then let's add the components, starting with the smallest one. We have a single 10 microfarad capacitor. Then we have a whole bunch of 100 nanofarad capacitors for each of the chips. And of course they fly everywhere. Then we have a resistor network for the flags LEDs, and we have a resistor array for the logic operation LEDs. Then we have a random 100 kilo ohm resistor, and a whole bunch of 15 kilo ohm resistors for other status LEDs. Then we have the blue LEDs for the flags. And then we have a whole bunch of green status LEDs. Then we have a single MOSFET. And in the same area a 74HC1G04 chip. Then we have a 74HC2G32 chip. And a 74HC2G08. And a 74HC2G86. Then we have a bunch of 257 multiplexers driving the outputs. Then we have an XOR gate. and a 151 multiplexer. Then we have a NOR gate and a truckload of multiplexers doing the shifting. And then the core piece of functionality are two 283 adder chips. And finally we have two buffers at the left and right hand side input. That looks pretty good. Let me solder this up. That looks pretty good. Let me add the sockets for the PLD chips. And then let me add the pin headers. This looks pretty good. Let me give this a quick cleanup off camera and then let's go test it. Alright, I've already got the CPU build back out and I've taken a closer look at the ALU PCB we've been building up. This is an older version of the layout, so I had to add a few botch wires, but thanks to the magic of editing, the schematic and layout you've seen me draw up at the beginning of the video is already updated and corrected. And now all that's left to do is to move the connections to the breadboard version of the ALU over to the PCB version. To get started, let me move the PLD chips over to the PCB. Let me start with the ALU decoder. And then the two chips that perform the logic operation. And then to temporarily connect stuff to the PCB until we have a backplane, let me just use a bunch of breadboards, same as we did for the program memory. And then let's hook stuff up. Let me start with the left-hand side input and the right-hand side input. Let me get rid of some of the power connections to the breadboard. Then let's connect the opcode. Then let's move over the output enable for the ALU result. And then let me connect the flags output enable of the ALU PCB to the flags write enable of the register file. And in a second we somehow need to find a replacement for the OR gate that used to drive this flags write enable. Then let me connect the flags read data output from the register file to the flags input of the ALU. And the flags output from the ALU to the flags write data input of the register file. And that just leaves the result. And then let me remove the remaining power connections and get rid of the breadboards. It's pretty cool to think that we managed to move all of this complexity here on the breadboards onto such a small PCB. We still need a power connection for the PCB. And now we only need a replacement for the OR gate that drives the flags write enable signal. If you remember, we're using that OR gate to disable writing to the flags register if we're not doing an ALU operation at all, or we're doing a conditional move operation. This is going to be temporary anyway, and we already have a breadboard with this random inverter. So let me add a 74HC32 OR gate chip. One of the inputs of the OR gate is already connected to the result output enable of the ALU. And the other side, I'm going to connect to the topmost bit of the ALU opcode. Now, if you remember, all our conditional move operations have the topmost bit set, which is what allowed us to disable writing to the flags when we're doing a conditional move. And then we're going to use the output of that OR gate to drive the flags write enable signal, which is also going to control the flags output enable of the ALU. And that's all there is to it. Let me power this up and let's see if things still work. Let me step the processor out of reset. Nothing caught fire so far. First up, we're going to clear the register file to 0, which worked like a charm, but the ALU wasn't involved in that yet. The flash chip still contains the conditional move test program, so let's try a few of the instructions. First, we're going to load 1001 into the first register, and then we're going to flag swap this value from the register into the flags register. And over at the ALU, you can see that the logic operation is set to the all ones value, which is the flag swap operation. And indeed, the flags write enable signal is enabled. We're reading the 1001 on the first read data port of the register file, and the ALU is forwarding the current value of the flags register to the write data port. So when I hit the clock, you can see that the 1001 is now stored in the flags register, and the first register contains the value that was previously in the flags. Now we're loading a 1 into the first register and perform a bunch of conditional moves based on the individual flags. The first set of moves occur on carry, not carry, 0 and non-zero, so we expect a 1, a 0, and a 1, which works. Then we're going to clean this up, and the next batch of moves is going to be on signed, not signed, overflow, and not overflow. So that's going to be a 0, a 1, and a 0, which also works. Pretty cool. Next, we're loading a bunch of values and perform unsigned comparisons. First, we perform the comparison, which is going to update the flags register. And then we're using a bunch of unsigned comparison condition codes to perform the conditional move. And we expect to see the 1, a 0, and a 0, which is exactly what happens. Next up, we expect a 0, 1, 1, 0, which also works. And finally, we expect a 0, 0, 1, 1, which also works. So it looks like the ALU PCB is actually working. At the end of the program, we're still computing the largest 16-bit Fibonacci number. So let me hit reset on the processor and run, and let's see if the largest Fibonacci number comes out. Pretty cool. This is still the number 46,368, the largest 16-bit Fibonacci number. So it looks like we managed to take this huge stack of breadboards that was here on the left and compress it down to this pretty compact ALU PCB. And this has made the CPU a whole lot cleaner and more reliable. We still have quite a bit of wiring mess around here because we need to transport data between the different parts of the CPU. But that will change in the next episode, since we now have a program counter, the program ROM PCB, and the ALU PCB. We're in good shape to actually draw up a backplane for these three PCBs and then hook it up to the register file. And at that point, the only wiring left over is going to be the clock generator breadboard down here and these random ICs that we're using to help decode the instructions. So at that point, we'll have a pretty compact CPU, which we can move to the side a bit, and we can start focusing on the instruction decoding, which is going to get rid of these integrated circuits and replace them with a proper instruction decoder. And I can't wait to finally close out this migration onto dedicated PCBs. So let's get to work on a pipeline backplane and getting rid of all of these wires in the next episode. Like and subscribe if you want to see more of this, and see you next time.